Welcome to P. Calc, Practical Calculus for the Busy Math Student, and in this video we're going to take a look at an example of finding the arc length of a plane curve defined in parametric equations. Here we're taking a look at the plane curve for the parametric equations x equals 6t squared and y is 2t to the third, and we're looking at on the interval as t goes from 1 to 4. So if we just take a look at our graph here, we can see that on this curve, when t equals 1, this graph is going to begin here at point 62, and then when t is equal to 4, we're going to have this right end point, and that is at point 96, 128. Although the interval for t is rather small, because of the parametric equations we see here on the scale, this is pretty long arc length. So the arc length in parametric form is derived and proven straight off of the arc length formula for a function, which is the integral of the square root of 1 plus f prime squared from a to b. And if you would convert that into parametric form, it's a fairly straightforward proof, and we come up with this formula that you can see the similarities in the format of it. It's that the arc length is the integral of the square root of dx dt squared plus dy dt squared as t goes from a to b. Notice here everything is functions of the parameter t, and sometimes that will be expressed as theta. It depends on what you want to use as your parameter. So the first part of finding the arc length is to determine what are dx dt and dy dt, which we sometimes can use Newton's notation here. We'll call these x prime and y prime. So x prime of t is 12t to the first, and y prime of t is 6t squared. So we do that first, and then we're going to go ahead and state our arc length integral by definition. Lowercase s represents arc length here, just as with functions, and t is going from 1 to 4. And so our integral is the square root of 12t squared plus 6t squared quantity squared. And we're going to integrate that with respect to t. Now, the inherent problem with arc lengths in general is that they tend to make integrals that are very, very difficult to do, or possibly not doable at all. So let's just see what happens here. So we can get to the bottom of this one. If nothing else, though, if you have a numeric integration technique available, you could figure out the arc length now. But I think we can get to this conclusion. So if we square everything out here, we have the square root of 144t to the second plus 36t to the fourth. So if you notice inside of the radical, in the radicand there's a common factor of 36t squared, which is itself a perfect square. So what I'm going to do is I'm going to combine a couple algebra steps here. I'm going to take a factor of 36t squared out of the terms in the radicand, and then I'm going to take the square root of that common factor, which gives me 6t to the first outside of the radical. And then on the inside, I'm left with 4 plus 1t squared. So from that algebra step, I can see now that I'm set up here. I see a du indicator, and I can go ahead and find this integral using u substitution. If I let u equal 4 plus t squared, then du is 2t dt. So if we go ahead and rewrite it in the u variable, now I need a 2t dt, so I'm going to take a factor of 3 out, so it'll be a 3 on the outside of the integral. And if we wish, we could go ahead and switch the bounds over into u also. If u is 4 plus t squared, that means that the lower bound is going to be 5. And the upper bound is going to be 20 in u. And then I'm left with, on the inside, u to the 1/2 du. And we'll integrate using general power rule. So that gives us 3 times 2/3 u to the 3/2. Again, since we're sticking in u here, the bounds are from 5 to 20. And we'll just simplify one more step. And then we can evaluate. So the exact value is going to be 2 times 20 to the 3/2 minus 5 to the 3/2, which is irrational. So we'll go ahead and we'll get a decimal estimate on that. And that estimate is it's approximately 156.53. And since we sketched the parametric plane curve here, we can see by the magnitude of the points that we know and the curve that we're looking at, that seems like a pretty reasonable result. So we'll go ahead with that. But that's a nice example of the arc length in parametric form with some algebraic parametric equations. If you'd like to learn more about the calculus of parametric equations, you can look them up in my textbooks available for a nice price on Amazon. Don't forget to subscribe to the page, and until next time, I'm P. Clark.